Okay, welcome back to Theorem Engineering. Now what I want to do is to look at Norton's theorem, okay? And previously you would have seen the video I did on Thevenin's theorem, okay? I'm trying to spit it out now. Right, Norton's theorem. Now, in this theorem, the network is replaced with a current source, IS, in parallel with a resistor RT. Let us consider the following circuit. And here you need to draw out your circuit, R1, R2, R3. Now here we have R1, which is 11,000 ohms, R2 at 22,000 ohms, and R3 is 47,000 ohms. And we have terminals A and B. Okay, we have our source supply here. Okay, so let me just get my pen. I love my pen because it makes me feel important, and I don't get that every day. Okay, so yes, I know. Okay, R1, R2, and as I said here just now, it's R3. Okay, and here's your source of supply. Now what I've found here is that I should have probably put a value of voltage here, but I haven't. Okay, so I must have done that for a reason. So hopefully I will see that reason as we move on. Now this would then become, so this circuit here, this would then become this simplified circuit, and this is our simplified circuit here. Okay, this here is our simplified circuit. Okay, so what did we do to get a simplified circuit? We had to determine the values of R1 and R3 because R1, R3 is in parallel. When you calculated these two values here, these two values would then be added to R2. So then that would then get RT, the total value. Okay, now let me see if what I've just said is what I did. Yes. To calculate RT, we must again use the formula. RT equals R1 times R3 over R1 plus R3. And let's just make sure we're using the correct ones. R1, R3. Okay. Now, you need to make sure that you have written out this formula. Do not ignore it. Okay? And don't think it's something you can just do in your head. I know some of you guys are brainy enough and so forth and think you can hold everything in your head. You can't. It doesn't work like that. Okay? So put pen to paper. Again, put pen to paper. Okay? You cannot go wrong. Okay? And all I'm doing now is here. Let me just see if I could bring in a highlighter in this case rather than a pen. Okay? Let me just bring in highlighters. Okay? I'm just highlighting this now. And here, now this is how I work, okay? This is just me. You might want to work a different way, okay? And here you have 517 times 10 to the 6 over 58,000, okay? And the value of that comes down to 8.913 kiloohms, okay? And again, make sure you work it out that you agree with my calculations, okay? Because I could be wrong. And I could just have done this just to confuse you. Okay. And here again to find the total resistance RT. And that's all I've said here. Okay, I'm not just showing you here what I did to get the total value here, because we did these two here. Okay, let me just highlight like that. We did him, and we did just these two. Okay, and all I'm now saying here is that we now have the resistance in parallel plus at the value of R2, and that's what we have here. Okay, giving us the total value of this circuit. Okay, in regards to its resistance. So this is not the final element here. Okay, let me get back to my pen. Okay, that's not the final element here, but what you can see here now, this is our final value here. Okay, when we take in both the parallel and the remaining resistor in series with the total network. Okay, now here we need to find the voltage at the open circuit AB. Okay, and here we have voltage open circuit. Okay, and here's what we are doing. Okay, now make sure that you can follow this information. Put pen to paper, put your pieces in place. Okay, don't ignore them. Okay, I work differently to you, so make sure you can understand what I'm trying to say to you, and that you arrive at the same conclusion as myself. Again, I could be wrong. I do not profess to be perfect. Okay, but at least if I'm going to be wrong, at least show me where I'm wrong, tell me what I've done wrong. Therefore, we can then look at it from that perspective. Okay. And here you have your current source. Okay, again, that's for you to confirm for me. You can see that what we're saying here, that this is the current source is generating 0.315 milliamps. Okay. Okay. Now I hope you found this useful. Let me just go back through it slowly and make sure that you can see it in full. Okay, let me go back a bit. Step back a bit. Okay. Let me take it to the top, from the top. Okay. Norton's Theorem. Okay. And I've spoken to you and told you what this is. Okay. Now this is my rough work. Okay, this is my actual work, my work that I've done myself. This is to make sure that I'm trying to illustrate and show the students the process to how we arrive at a given solution, and that you can't miss out pieces. Now some of us can miss out pieces. I remember sitting in class and these guys were doing fractions in their heads and just putting down the number like 2, 4 or 10, and I'm trying to figure out how the heck to get those figures when you needed to show you're working out. And that is one thing I never quite understood. We didn't need to show the working out. They just put down figures, numbers, and that was it. I could not work like that at all. I found that rather disturbing for me, but then again, that was just me. Okay, I hope you found this useful. Again, have a good day. Bye bye.